More than 100 years ago, in 1915, Albert Einstein wrote down the well-known equations of general relativity, which describe one of the fundamental interactions in nature, the gravitational interaction. The gravitational interaction is the most familiar to us. It makes apples fall and solar system planets orbit the Sun, for example. Einstein's theory states that space and time are inextricable link, forming what is known as space-time. Space-time is distorted in the presence of massive objects, such as a planet or a star. It is this distortion, the curvature of space-time, that we perceive as variations in the gravitational force. These astonishing ideas are encoded in Einstein's equations. They capture how mass and energy warp space-time and, on the other hand, how the curvature of space-time bends the trajectories of light and moving objects. After Einstein's theory has been published, physicists and mathematicians start looking for solutions of these equations. It was soon realized that some of them describe quite intriguing objects, nowadays known as black holes. Objects so massive that they attract and trap everything, including light, within a certain region of space-time, enclosed by a surface known as event horizon. Once an object crosses the event horizon of a black hole, it can never escape from it. The event horizon is definitely what a black hole is all about. However, it is not physically possible to detect an event horizon and therefore have a direct proof of the existence of black holes. This means that physicists can only hope to infer the existence of black holes by observing the neighborhood of extremely dense objects which may be black holes. If a sun-like star passes close to a black hole, for example, then stellar material flows from the star to the black hole and forms an accretion disk. If the star and the black hole are sufficiently close to each other, they become gravitationally bound and form a binary system. Matter particles in the disk emit light that can be detected by ground or space-based telescopes. This light provides useful information about the object around which matter particles swirl and whether it fits the features of a black hole or not. But binary systems are not just light sources. Besides light, they produce gravitational waves, small ripples in space-time also predicted by Einstein's general theory of relativity. The first observation of gravitational waves was made in September 2015. The waveform matched the gravitational wave signal emitted by two merging black holes. Despite the wealth of experimental evidence which supports the existence of black holes, physicists cannot assert that all these light and gravitational wave signals are coming from black hole systems. In fact, some exotic compact objects can mimic the behavior of black holes, although they might be very different from them. They even might have no event horizon. Current observations are not precise enough to discard most of the black hole alternatives. For this reason, the way these exotic compact objects interact with light and matter has seen a renewed interest over the last decades. In the coming years, precision gravitational wave astronomy will certainly constrain black hole alternative models and therefore support or deny the existence of black holes. I am currently studying some of these exotic compact objects for my master's dissertation, entitled Exotic Compact Objects Interacting with Fundamental Fields, under the supervision of Professor Carlos Herdeiro and of Professor Vítor Cardoso. Thank you for watching.